B has to be 0. So A cannot be a 0 divisor, and that's why JP has no 0 divisor. JP has no 0 divisor, and this completes the proof. By the previous lemma, this now says that JP is a field. The above corollary says that we have infinitely many fields, each having a finite number of elements. Because the number of primes is infinite, so for each p, JP is a field. So that's how you will get infinitely many fields having finitely many elements, each one of them. So they are naturally enough called finite fields. The JPs are not the only finite fields. There are others also. They do not exhaust the collection of all finite fields. In fact, towards the very end of this book, in the 7th chapter, specifically in section 7.1, we shall give a complete description of all finite fields. That is, we shall see the general structure of a finite field. That sort of results we have 2 or 3. We also have a result that tells us how finite abelian groups look. Okay, complete description of finite abelian groups, or in fact even finitely generated abelian groups. So some such results are available. Okay, now so this there goes this question of having JPs as fields. Right. Now there is one more point that comes after this. That is this observation. There is one particular difference between finite fields and fields such as the rational numbers, the real numbers, the complex numbers. here more familiar. And what is that difference? Let's look at it here. Let F be a finite field, any finite field, okay? F is any finite field with, say, Q elements, where Q is some positive integer. Considering F as an abelian group under addition, because every field, in fact every ring is an abelian group under addition, we have by that result, where what is the now by corollary to, it's a result from group theory, by corollary to theorem 241. This is Lagrange's theorem from group theory. Corollary 2 says that it's that familiar result. If you have a finite group G, say having m elements, or where order of G is equal to m, then if you choose any element in G, then this power is equal to identity. It's that result. So now in place of that any group, any finite group, we have the additive group in the field, which in this case is finite because the field is finite, and there are how many elements? Q elements. This, we have this. A plus A plus A, etc. plus A, which is equal to how many A's? Q terms, which is equal to QA is equal to 0. Now look at this carefully. Okay, what is this A plus A plus A plus A Q times? In the notation of group theory, this is nothing but A to the power Q. A is any element in the field, okay, not necessarily non-zero or anything. A is any element in the field, and according to group theoretic notation, this is nothing but this. And actually that's why we have written QA. There is a meaning to QA. In an abelian, actually QA is nothing but A to the power Q. And this is equal to identity. Now for us the identity is 0. So this makes sense in the additive group of the field. For all A belonging to F, this does not happen in the familiar fields of rational numbers or say complex numbers or real numbers. And this observation prompts a new definition, actually two definitions which are in a sense related. and here is the first definition. Let R be, or let me use D. Let D be an integral domain. Okay, so D is a non-zero commutative ring with no zero divisors by definition of an integral domain. We say D has characteristic 0 if the relation MA equal to 0, where A is any element in D minus 0. Okay, so A is any non-zero element in D, and M is any integer can hold only if M is equal to 0. So this is, that's how these rings are, which are our usual fields of rational numbers, complex numbers, real numbers. They are fields because fields are integral domain, also integral domain. So these particular integral domains are of characteristic 0. What is the meaning of this definition? The meaning is that if we take any non-zero element A in the integral domain and we take an integer M and we compute this MA. Note that M is an ordinary integer and A is an element in the integral domain. So MA has a specific meaning, and the meaning comes from group theory. MA is nothing but A to the power M. That has to be made sense in this additive group. Okay, so M can be any integer. In group theory, we have a meaning for A to the power M, where A is any element and M is any integer. But for now, of course, A is non-zero. So this relation can be true only if M is equal to 0. What is the meaning of only if? It means that if I assume this, where M is an integer and A is a non-zero element in D, then that implies M is equal to 0. If this happens in an integral domain, we say that it has characteristic 0. So these are some examples. Opposite to this, there are integral domains of finite characteristic.